never had that before.
Yeah, it just asked me if that was okay.
Wow. Good afternoon. We're going to do work on some worksheets for chapter 5 today, the live session. And I will always, just because we have a smaller class this summer, I'm always going to attach the link to the live sessions from the winter class. That way you've got some variety too on worksheets. But let's just go over some dates. Someone just asked about the midterms. So let's see, we are in week 3 today. There were chapter 4 worksheet is due tonight. You had some my stat lab due last night. Wednesday is a chapter 4 project. There are no projects for chapter 5, but there are 2 worksheets. In your course pack, there are 3 worksheets, but I'm only assigning parts of 2 of them, and you'll see the pages. I have them. Make sure you're reading everything detailed in the assignments. They're due on Friday night. And then next Monday is Memorial Day, but because it's a 7-week course, I still am just leaving everything the same. My stat lab is due Monday night, so just if you want to get it done early, you can do that. If you have questions, and it'll just be a small penalty if you turn them in on Tuesday or something. Chapter 6 review worksheet is due on Monday. Let's see, we have the midterm scheduled for next Thursday, but let me see here. I am debating on pushing it back to Tuesday, the 8th of June. But if I do that, I just don't know if we'll have time to get everything in. So that's worrisome. Yeah, I think I'm going to have to leave. We'll see here. I might end up pushing the midterm back to Tuesday, the 9th. I'll send something out the next day or so. I'm just kind of debating on that still. But we would still have the live class on Thursday, and I would still leave all the chapter 7 things. What I would do is I would have a live class on Thursday, the 3rd, with if anybody wanted to come with extra review / I would work on chapter 7 items so that we still get ahead the same. I would just swap that Thursday for Tuesday for the midterm to give everybody maybe the weekend to study because of Memorial Weekend. So I'll send out more information about that. All the dates are in JetNet, as well as our final week goes usually Monday to Sunday, but because there's one last day, Monday the 28th left, I may give some weekend times for that final on June 28th because I'm going to be out of town on that, but I'm still available for the final. I just got recording times on that. Okay, so let's look at some review here on the chapter 5. Hi, Monica.
Hello.
So everybody has their chapter 5 out. I would like to, as we get going here, I am going to address this chapter 5 review worksheet number 2 once we get there. But I would first like to look at the 5.1 worksheet number 3. So page 491. Talking about the rules of probability. So let's just go here. Oopsie, nope, I'm not to share my screen. Okay. So 5.1 worksheet 3, page 491, rules of probability. So probability can come in a couple of different forms. You learned in the YouTube videos. It can come as a percent, it can come as a decimal, it can come as a fraction form. I'm usually pretty flexible at how you give that to me, preferably a decimal or a percent. And there are a couple of rules on probability that we learned in the YouTube videos, whereas probability distribution. So i.e. all the outcomes of a probability scenario, they have to add up to 1, and each of the individual probabilities has to be bigger than 0, greater than or equal to 0, and less than or equal to 1. So both of those have to be met. So that's gonna come up here in the worksheets today. Thought I would throw those 2 big things out there. So number 1 here says a shopping mall has set up a promotion as follows. With any mall purchase of $50 or more, the customer gets a spin on the wheel shown below. List the outcomes in the sample space. So we always put outcomes in brackets, and it looks like they could land on any number 1, 2, 3, or 4. But we can quite quickly see that some of the numbers come up more than others, right? So 1 only happens twice, 2 only happens once, and then 3 and 4 happen many other times. So it says if a number 1 comes up, the customer wins $10. If the number 2 comes up, the customer wins $50. If the numbers 3 or 4 comes up, the customer wins a discount coupon. So that's why 2 is so special, because they win $50 and there's only one time that can happen. So B says, what is the probability of a player winning a discount coupon? Give 3 decimal places. So a discount coupon would be a 3 or a 4. So that would be probably of a 3 or a 4. And this also brings up the idea of an or situation. And so kind of bringing up our course pack here. And it doesn't come up to 5.2, but it kind of comes up here as 3 and 4 are mutually exclusive, right? Meaning that they can't happen at the same time. So that comes up in 5.2, but it kind of applies here in this 5.1 worksheet. So because we can't land on a 3 and a 4 at the same time, we can just add them together. So any of the 3s and 4s count. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 of the spots, and there are 11, 12, 13. I believe there's 13 spots. They counted correctly. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yeah. So 10 out of 13 are going to be where the customer wins just a coupon. And so that would be, it says 3 decimal places. So that would be 0.769 or 76.9%. Would winning the $50 prize be unusual? Okay, so I noticed some folks in the chapter 3 review worksheet as I've been grading those. I'm almost done with those and getting caught up on and ahead on the chapter 4 items as well. But when I was looking over the chapter 3 review worksheets, some folks were not using the unusualness like we talk about it in class. So it makes me wonder, make sure that you are watching the videos and thoroughly watching everything that we're working on, because to be unusual, this outcome would need to be less than 5%. So to win the $50, that means they have to land on the 2, which only comes up 1 time. So that would be 1 out of 13. And that percent is 0.0769, which is 7.69%. Which is not unusual because it's greater than 5%. Okay, so that goes back to some rules that we talked about in chapter 3. Any questions so far from folks? Okay, number 2 says, the table shows the proportion of active duty military personnel in the 4 main military branches from 2018. Fill out the table appropriately. Give 3 decimal places where necessary. So when we find probability, it's always the individual outcome frequency divided by the total frequencies. And that is the same in the chapter 3 review worksheet as well, as looking some of those over. So we have to know how many total here in our frequencies. So you can go ahead and add those up. So it looks like when we add these up, we get 163,582. And so to find this probability, we take 63,519 and divide by the total, 163,582. And when we do that, we get 0.388. And then likewise, we're going to do the rest with the following. So 0.237. So making sure that we have 31310. Oops. Divided by the 163,582. And that one comes out to be 0.191. And then 0.183. Okay. Any questions on those? Okay. So the next page gives us an opportunity to see if we understand what makes a valid probability model. And I mentioned earlier, just a few minutes ago, what it takes. There's 2 rules. And I'm going to let you pause the recording for a moment and just mark yes on each of these and no if it does not meet it and why. So make sure that on anything in the review worksheets, midterm or final, if it says why or explain, I'm expecting an additional answer. So I'll let you work on those for a moment. Okay, so on the first one, the outcomes are all positive. The probabilities are all positive. So we're good there. However, they do not add to 1. So because this means some, they add to 0.95. So they don't add to 1. Then in the second one, that one, sometimes people have a little question on because this outcome says -50, but our outcomes could be negative, right? It could be a question of making money or losing money. So you could lose money. It's just the probability has to be positive. So these all add to 1 on the probabilities and they're all positive. So that one is a yes. And then the third one is a no because there is a negative probability. So the individual probabilities have to be greater than or equal to 0 and less than or equal to 1, and they have to add to 1. Okay. So question number 4 is fun. It kind of gets us thinking about the different probabilities and what they mean in a particular situation. And so it says someone computes the probabilities of several events. The probabilities are listed on the left and some verbal descriptions on the right. Match each probability with the best verbal description. Some descriptions may be used more than once. Okay. So I'm just going to kind of look at some of these descriptions here. This event is certain to happen. So certain to happen means that it's definitely going to happen. So I would say that that would be D, this probability 1, right? It's most certain to happen. This event is as likely to happen as not. I would think of that as like a 50-50, right? So That would be this one up here, 0.5 or 50%. Let's see. This event may happen, but is not likely. So not likely, well, 0 would be it's not going to happen. So that would be 6. This event cannot happen. I would say that one would be 6. 4 says this event is very likely to happen, but it is not certain. So we're very likely means it's got a high probability, but it's not 100%, right? So I would say that would be the 0.9. It would be unusual for this event to happen. And remember, we said unusual is less than 5%, so less than 0.05. And that would be G, this one here. This event cannot happen. So we said cannot happen would be the 0 one. And I mean, cannot happen would be, it can't be negative and it can't be a 2, but that could also be the made a mistake thing, right? So the someone made a mistake would have to be, I think, this one and this one, because you couldn't have a negative and you can't be over 1. So I think that would be that. And 10, let's see, 10. This event may happen, but it is not likely. I would think that 3 would be a good one for that. So the descriptions are kind of how we refer to things in our everyday life, right? And so we kind of should associate those with number values over here. So let's look at number 5. It says the following box plot shows the audience size on Instagram by country in 2020 in millions. You're going to select a country at random from this data set. Okay, so this is for Instagram users by country. What is the probability that the country has more than 18.5 million Instagram users? So 18.5, we're going to go down here on the horizontal and estimate where 18.5 would be. And 18.5 looks like it matches up with this value right here. Now remember that this is a good review, right, of chapter 3 in our box plot. That bar in the middle is always Q2, or we actually refer to that as the median, which means that 50% fall below and 50% fall above. So more than 18.5 would be 50%. And then B says, what is the probability the country has less than 37 million Instagram users? So let's find out where 37 is. So there's 30. 40, and the bar in the middle is 35. So it looks like if we bring this right hand side of the box down, that's right about 37, and it was less than 37. So this right here is our Q3. And remember, Q3 marks where 75% of the values are below that. So 75% of the countries. Any questions on this one? Next up, this is kind of a big one. Let's kind of go over the overall, and then I'll have you pause the recording and take a few minutes and work on it. So the section of an exam contains 4 true and false questions. A student who did not study takes this exam and randomly guesses on these 4 questions. Using the multiplication rule, how many different ways can 4 questions be filled out randomly by the student? Okay. How many different ways can 4 questions? So each question has 2 outcomes, right? True and false. And so in the course pack, we talked about how much is in our sample size. And we did this in right about page 141 in our course pack here. And we talked about determining the sample size. And so P, Q, and R are the number of ways that each of the outcomes can happen. Okay, so we have question 1. So I'm going to label them question 1, question 2, question 3, and question 4. And there are 2 ways that each of them could come out, right? True or false. So 2, 2, 2, and 2. And because they are independent of each other, the answers, we can use the multiplication principle. So there should be 2 to the 4th or 16 ways that a student could randomly choose these 4 questions. So construct the sample space using a tree diagram. Okay, so using the tree diagram, we've got question 1, right? Question 1 could be a true or a false. A false. Okay. And then question 2 would be a true or a false. So they could have done true and true, or true and false, or they could have guessed false and true and false and false. And then we have the third question. And it stems from each of these, right? So the third question could also be true and false. And then the fourth question could also be true and false. So true and oh geez. My drawing skills are not great. Never estimate this correct to have enough space. Now, the final sample space is not this. The final sample space is listing out the sequence for each of these 16 ways. So you should end up with 16 leaves here at the end, basically. So the first one is really the sequence of true, 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 and true. And then the second one is true, 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 and false. And then the third one is true, true, false, and true. And then the next one is true, true, false, and false. And then we have true, false, true, 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 false, true, false. And we have true, false, false, true, and true, false, false, false. That's the first 8. And those all have true as the very first question. And then the second 8 are going to be identical, except for the first question is going to be all false. So I'll do those in green so you can see the difference. So it's going to be false, and then true, 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 and then false, true, true, false, and then false, true, false, true, false, true, false, false, then false, false, true, true, false, false, true, false, then false, 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 true, and then the last one is all false. Those are the 16 different sequences that could come out of those 4 multiple choice questions or true and false questions. Take a minute and make sure that you have the same 16 I do. It says, assuming the outcomes to be equally likely, find the probability that all the answers are false. Well, there's only one of those, right, where that happens, and that's this last one. So this probability is just 1 out of 16. It says just give the reduced fraction. The second says, assuming the outcomes to be equally likely, find the probability that exactly one of the 4 answers is false. So exactly one of them is false. So we have that one here, right? Here's one where exactly one is false. Here's one. This one doesn't count because it has 2 of them that are false. This one only has 1 false. And it looks like this one here is the only one down here where there's only 1 false. So there's 4 out of 16. And so that reduced fraction would be 1/4. Then the last question says, assuming the outcomes to be equally likely, find the probability that exactly 2 answers are true and 2 answers are false. So exactly 2 answers are true and 2 answers are false. Okay. So I'm going to use my highlighter just so I can mark them in a different way. So true, 2, and true, false. So it looks like this one here is 2 true and 2 false. 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 2 and 2. 2 and 2. So it looks like 1, 2, 3, 4, 5, 6 of them. So 6 out of 16, and if we reduce that by 2, we get 3/8. So you can see. Okay, so 3/8 is our reduced fraction on that one. Questions on that one? So let's go back to our lab here. So that was 5.1 question worksheet 3. Let's look at 5.2 worksheet number 3, so page 498. So 5.2, we're getting into the or situation, or mutually exclusive events. So 498. And I already brought up the definition of mutually exclusive, but we can most certainly bring it up again here. So if we go to something else we didn't really talk about in lesson 5.1 is that there are 3 different types of probability. One is called classical probability, and that's one that's based on equally likely outcomes. So the overall event isn't always equally likely, but they're based on original equally likely outcomes, like rolling a fair die, drawing out of a deck of cards, a true and false, something like that. Okay. And then a simple event is where there's only one outcome that could make that event true. And so those were a couple things that we didn't touch base on the worksheets. So let's look here at this worksheet for question, oopsie, for lesson 5.2, and make sure everybody's there. And I'm gonna let you read these 2 questions here at the top on page 498. So it says determine whether events A and B are disjoint. That's mutually exclusive, which means that they cannot happen in the same event. So selecting a registered voter The voter is a mother and the voter is Democrat. Can you be both? The voter's mother and the voter is Democrat? Yes, so they are not mutually exclusive, or they're not disjoint. And then the second one says, selecting a single voter on election day 2020, the voter drives to the polling station, the voter bicycles to the polling station. Well, you cannot drive to the polling station and bicycle to the polling station unless you go twice, right? So they are disjoint. Okay, yeah, that's kind of that seemed like a funny question. So why don't you look over the next one here? It says, as a part of an experiment, subjects have a random fruit flavor additive placed in their water. The spinner to the right is used to determine the flavor for each participant. Note the dotted lines show equal sections of the circle. So you'll see here on your paper that there's some dotted lines here. So that will tell you that apple happens half of the time, right? So it says, are the outcomes in the sample space equally likely? That's a question. I'll let you think about that for just a moment here. Are they equally likely? The outcomes themselves are not. And that's no, because apple is more likely than both, right? And then grape is more likely than peach. And you can see that because any of these three spaces get landed on, and that apple is the additive. So what is the probability that the participant gets peach flavor? Well, it looks like there are 8 possible little sections they could land on. And so that would be 1 out of 8. So probability of peach. Notice that when we write a probability, we always do a big P for probability and then the outcome inside the parentheses. And so that would be 1/8. What is the probability that the participant gets grape or peach? So grape or peach, and they are mutually exclusive, so that means we can just add them. So grape or peach is going to be the same as saying probability of grape plus the probability of peach. And so grape is 3/8 and peach is 1/8. And so together they make up 4/8 or 1/2. And then D says, what is the probability the participant does not get grape flavor? So at the end of 5.2, let's take a look there. At the end of 5.2, we bring up the complement rule, and this is a great time to use it. So the complement rule says the probability of the complement is the same as the probability of not E. So 1 minus the probability of E. So we have a complement, right? Not grape. So the probability of not grape is the same as the probability of grape complement. And so we could just say, well, let's just subtract away. If we want everything but grape, we could just subtract away the grape. So 1 minus the probability of grape. So 1 minus 3/8 is the same as 5/8. So in this case, not grape and just counting on the spinner might just be as quick, right? 1, 2, 3, 4, 5. But when we're in a big situation where we may not know all of the outcomes that are not grape, sometimes it's easier just to use the complement rule to do that. So this worksheet here is, this problem is actually using a two-way table. So it says a poll was taken of 121,973 people between the ages of 15 and 44. And we asked them their gender, so male or female was, they had to answer. And then if they had insurance, if it was private, Medicaid, other, or if they were uninsured. So by answering the two questions, they could have fell in this category here where they were male and had other insurance, and there were 769 of them. Okay, so first thing we need to do is finish filling out the table. And so if you added up all of the males, there were 60,518. And if we added up all the females, there were 61,455. And then we needed to add up each of the categories of insurance type. So 83,867. And then 99,524. 1909. And 26,673. So it says a person is selected at random from this group. The person is male. So they want us to find these probabilities, give 4 decimal places. So the person is male would be anybody in this category here. So 60,518 divided by the total 121,973. And because we're not talking about conditional probability, which we would talk about if we were doing extended chapters or extended sections in chapter 5, but we're not. So these are all going to be basic probabilities out of our total, okay? Because we didn't say they had to be male first. So this was just a person was male. This comes out to be 0.4962. And what is the probability the person is uninsured? So that would be everybody in this row here. And we get 0.2187. And it says the person is not uninsured. So not uninsured would be the probability of uninsured complement. Remember, we just mentioned that on the last worksheet page. So the person is not uninsured. So that means we can use the complement of 1 minus the probability of being uninsured. And so we get 1 minus what we just had up here, right? The 26,673. So 1 minus 0.2187 equals 0.7813. So the complement comes up quite often. E says the person has private insurance or Medicaid. So private insurance or Medicaid. So can they have private insurance and Medicaid at the same time? No. So these are considered disjoint. So because they can be considered disjoint, we can add them together. So the probability of private plus the probability of Medicaid. And when we add those together, we get 9331. Okay, then F says, what is the probability the person is male and has private insurance? So male and private insurance is not disjoint, right? They have some overlap. Not disjoint. So male would be all of these people, right? And then private insurance would be all of these people. But it says that they have to be male and private insurance. So it's only this particular cell where these crisscross right here. So that would be 41,209. And then that comes out to be 0.3379. And then the last question says the person is female or has private insurance. And this is an or, so the not disjoint comes into play here. This is not disjoint either, right? Because they could be female and have private insurance. So again, not disjoint. So when it's an or, we can't, and we add them. So the probability of female plus the probability of private insurance means that we have to subtract away the overlap. So the probability of both. And then in my videos, I always call that the overlap. So the probability of being female was 61,455 plus the probability of having private insurance are these people here, 83,867. Subtracting the overlap. So I'm going to circle that in red. Private insurance and female. So we're going to subtract away that group because we can't have them counted twice. 42,658. So when you add those two groups and subtract away the overlap, you get 102,664. And that probability comes out to be 0.8417. Any questions on that one? Any questions so far? Are you guys both good? Okay. Do you want to do this last big problem that is like another whole kind of one of these scenarios, or do you want to move on to something in 5.3? It's kind of up to you when you're on the live session.
I don't care. I'm okay with skipping if the other one is, whoever else is on.
You said what, honey?
I said I'm okay with going to 5.3 if the other person is okay with it, if there's somebody else on here.
Arshna, are you okay going to 5.3, or do you want to do this one big problem here?
We can go to 5.3.
So let's see. So make sure we get the variety that you all want, because I'm going to post a link from the winter section anyway. So
Okay.
let's see what worksheet I had for 5. So for 5.3, I had page 505. And this gives us some card playing. So actually, do you ladies have page 501 and 502 there as well?
Yeah.
Handy. Why don't we get those out? Because the 505 is on the other video I'm going to link up. And this probability stuff is really tricky for folks. I thought I might do a couple extra different problems on our live one today. So page 501, let's look at a couple of these. And then I'm going to look at the chapter 5 review worksheet number 2, where we're rolling a 2 6-sided dice, so I can make sure everybody's getting that table filled out correctly for their worksheets, because that is always very tricky. Oopsie, did not need to. Don't need any of that. Oops. Okay, so let's go ahead and let's look at these problems here on page 501. We've got some extra time per chapter for 5.3. So it says determine whether events A and B are independent or not. So 5.2 was all about being disjoint, which is within one trial, can these outcomes happen at the same time? Independence usually is discussed when we're talking about a sequence of trials. So the trial happens, and then the trial happens again, or the trial happens and then something else happens. Okay, so like a sequence of events would be, I fell off my bike and then I broke my leg. So for me to break my leg, I have to fall off the bike first, right? So it's a sequence of events. What is the probability that I'm going to fall off my bike? And then what is the probability that I'm going to break my leg due to falling off the bike? So let's look here. Question number 1, it says, decide if they're independent or dependent. So having a large shoe size and having a high IQ. So it doesn't mean that one causes the other, but if one happens, does it change the outcome of the other? So if I have a large shoe size, does it change the likelihood of me having a high IQ? No. What would you say on there, Kevin? I would say that'd be independent.
Yeah.
That's a good silly one. Okay, what about the next one? Says a father is left-handed, his daughter is left-handed. So if a father is left-handed, the likelihood of the daughter being left-handed does change, right? Because being left-handed is hereditary. So that one would be a dependent situation. Now, on the worksheet that we were going to look at, page 505, or actually, this is another good one. On page 503, this worksheet, there's a couple other ones that are independent and dependent. So if you have that page there, we can look at these two, because these are the trickier ones, is independent, dependent. So it says selecting a king from a standard poker deck, not replacing it, and then selecting a queen from the deck. So not replacing always causes a form of dependence, right? It changes the likelihood of the next card. B says a student tossing a coin and getting ahead, and then passing a quiz in her English class. Those two things should definitely not be dependent on each other. They should be independent. C, driving over 85 on the highway and then getting into a car accident. Well, driving fast on the highway doesn't mean you're going to get in the accident, but it does change the outcome. It changes the likelihood of getting in the accident, right? So those are dependent. And D says randomly selecting a classmate to join the study group, and then randomly selecting another student to join the group. So randomly selecting one classmate and then selecting the other. What do you think on that one? That gets a little trickier because after you've selected the first person, you have one fewer person to select, right? So that causes those to be dependent from one another. Okay. So back to page 501, let's look at question number 2. It says a coin is flipped and an 8-sided die is rolled. So we have a sequence of events. The 8-sided die has sides 1 through 8. Find the probability of getting a head on the coin and a 4 on the die. So the probability of a head and a 4. So the probability of getting the head, they should be independent of each other. So we should be able to multiply them. So probability of getting the head is 1/2 multiplied by getting a 4 on the die. So that would be 4 out of 8. Oh, I'm sorry. I wrote myself a 4. There's only one way you can get a 4. That's 1 out of 8. That's what I meant to write. Sorry, I was writing while I was talking. So 1 out of 2 ways to get ahead and 1 out of 8 ways to get the number 4 on the 8-sided die. So you would have 1 out of 16 ways to get that. Look at this next one. The next one says, in 2018, 73% of US households had cable TV. You select 3 households at random. Find the probability that none of the 3 households had cable TV. Okay, so none of the 3 households would be the probability of no, no, and no, right? None of the 3 have cable. And so that could also be the probability of no cubed, because it's the same outcome happening 3 times. Because notice that n equals 3 here, because we have 3 trials. And so not having cable TV is going to be 1 minus the 73%, because these are the people that had cable. So this would be 1 minus 0.73 to the 3rd, or 0.27 to the 3rd. And depending on what calculator you're using, I'll show you what it looks like on the graphing calculator. So 0.27. And if you're using the TI-84 or using Desmos, you're going to use a caret key. So in Desmos, it looks like this as well. On your TI-84, it's just above the division key. So you're going to use that key. And then you're going to put in a 3. And it comes out to be 0.0197. Pretty small. B says, what is the probability the first household has cable, but the second and third do not? So probability of yes, no, no. So that would be 0.73 for the first, right? And then 0.27 squared. So I wrote a 1 on the 0.73 because if you make sure you add 1 and 2 to get 3, then you know you've taken care of all 3 outcomes that you're running in the trial, because there were 3 households. And so this would look like 0.73 parentheses 0.27, and then you're going to square that. So this one is 0.0532. C says, what is the probability all 3 households had cable? So This is kind of just the opposite of A, because this time it's the probability of yes to the third. They all had cable. So that would be 0.73 cubed. And that comes out to be 0.3890. I'm going to try that in your calculator. And then D says at least one household had cable TV. So the at least one rule, let's get out our course pack and make sure that we are acknowledging where the at least one rule happens. And that is on page 156 and my course pack is 156. Yours might be a little bit different. Your course pack should be correct, have a corrected piece here. Is yours corrected? It says
Yeah,
one minus not, okay. So page 156 should have this at least one rule. So at least one E and N trials. So whatever your N trials are, that's going to be your exponent. And so that means we're going to do one minus the probability of E, and that probability is getting raised to the N. If you have not watched all of the YouTube videos, this will definitely not suffice. You want to make sure you watch them because I go through more examples in the course pack. So we want that at least one of the households had TV. So it could be one had TV, two had TV, they all had TV. It could have been different ones having the TV, right? So there's all of these different ones. So we're going to say the probability of greater than or equal to one cable is equal to one minus the probability of none, right? And so that would be the probability of none to the third. And we already know that that's up here, right? 0.0197, but we can write it as one minus that. So one minus not having cable. So that would be one minus 0.73. So it's a complement within a complement on this one. These at least ones get tricky in some ways. So one minus the 0.27 cubed is one minus 0.0197. And that comes out to be 0.9803. So 98% likelihood that at least one of those three households has cable. Any questions so far on that one? Okay. We've got some cards. Some card problems. Before we move on to other problems, I do want to spend a minute and have everybody get out. If the people on the live session have, why don't we take maybe like a couple minute break, and when we come back, if everybody could have out their second worksheet, it's page 511. And we're gonna make sure everybody gets the sample space constructed going correctly, because it's a little bit complicated. It's the ones that I went through in the YouTube videos where you're playing craps at the casino, or Monopoly uses the same thinking. You're rolling two dice, right? And you're adding those two dice. So you could have a minimum sum of a 1 and a 1, which is a 2, or you could have a maximum sum of a 6 and a 6, which is a 12. And if anybody's played Settlers of Catan, I really want to learn how to play that. I have it, but I don't. Do either of you know how to play that game?
no.
I have it, but I've not ever played. So everybody good taking me just a couple minute break, and then stretching, grab a snack or whatever. We'll come back and we're gonna make sure everybody has this filled out on the live.
Okay.
For the recording. Okay. So let's look at this. It's page 511 in your chapter 5 review worksheet. Number 2. And I'm going to go over that. And this is this one. Okay. So this is one of the worksheets that you're turning in. It says there's 2 6-sided die. How large is the sample space? So we have the outcomes on die 1 and we have the outcomes on die 2. And they each have 6 and they should be independent of one another, right? So we should be able to multiply them. So there should be 36 outcomes. And then I'll let you all explain why we would not want to make a tree diagram of these 36 outcomes. I think that's pretty self-explanatory. Okay. And so it says construct a sample space for this probability experiment. So we're not going to do the whole tree diagram, but we do have to have the sample space. So we're going to look at die number 1 has a possibility of, I'm going to draw them up here, 1, 2, 3, 4, 5, and 6. And die 2 also has 6 possibilities. So I'm going to do those along this column here on the outside. 1, 2, 3, 4, 5, and 6. So unless the die are 2 different color, it's hard, you would think, you know, if they're both 2 white die, it'd be hard to tell which one, when you roll them, right, which one is the one, and if they're both ones, like which one is which. So I'm going to treat them as if I know that one is green and one is red, so I can keep my eye on which one is landing on which number. So I could have this possibility, right, where they each have a 1. And so I'm going to carry this first die with a 1 all the way down here. So the first die could get a 1, and the second die could be a 1, a 2, a 3, a 4, a 5, or a 6. And then the second die could be, or I'm sorry, then we can go back to the first die. Well, what if the first die was a 2? And the second die was a 1, a 2, a 3, a 4, a 5, or a 6. And then likewise, the third die, I meant the first die could be a 3, not the third die. The first die could be a 3. The first die could also be a 4. It could be a 5. Or it could be a 6. And then, so my green is always going to be my first die, and my red is going to be my second die. Okay. So now that we have our sample space filled out, we need to look and see that there are some patterns or some things that are occurring here that are interesting. We do ask the question, what is the assumed probability for each outcome in the sample space? So there's 36 in the sample space, and each of these are outcomes. So I'll need to answer that question. But I do want to get you to starting this table here. Because there's 36 outcomes, but there's only certain values that the sum of the two dice can be. So we already mentioned that the lowest sum could be this very first instance right here, this 1 and a 1, right? So you could have the sum of 2. Because this is what do they add up to be. So there's only one of the 36 times when you can get a 1 and a 1. So that probability is 1 divided by 36. Then we ask ourselves, what is the next sum? Well, I could get a sum of 3, right? And how many ways does that happen? You can see that it happens either we get a 2 and a 1 or a 1 and a 2. So there's 2 out of the 36 times that happened. So I'm not going to fill in this whole table, but I want you to see the next one. The next one could be a sum of 4, right? Now this could happen a 1 and a 3, or it could be the 3 and the 1, or it could now be the 2 and the 2, right? So we've got another double, because remember when you get doubles on Monopoly, there's special things that happen. Okay, so for that one, for the sum of 4, there's 3 out of 36. So you're going to continue to fill out that table. My video from winter has, I think there's more of that table being filled out, so you want to check that out. Arshna, any questions so far?
Good.
Yeah, you're good. Okay. So to kind of go back to more of these probabilities and reading a two-way table, because I want to make sure that you're prepared to work on these worksheets this week. I think we could spend our last minutes together going back to the 5.3 worksheet number 3, page 505 that I had originally had in the Google Doc. Okay. So let's look at number 1, and then I'm going to jump to the next page. So I want to make sure we get as much done as we can before you have to leave. Okay, number 1 says, determine whether events A and B are independent or not. A JC student is chosen at random. The student is average height, and the student's mother is average height. So the student being average height, is there, does that affect the possibility of the mother being average height? Or really it's more like the mother's being average height, right? It has changes the probability of the student being average height. So they're definitely a dependent situation. Not necessarily that one causes the other, but one does change the probability of the other one occurring. So B says a JC student is chosen. The student was born on a Sunday and the mother was born on a Sunday. Do we think that these are dependent or independent?
Independent.
I think the stars just aligned, right? That's what we would say. Is there something, maybe it was a full moon. So no, they're definitely an independent situation. Okay. So I would like us to go to page 506. And I would like us to work on questions 3 and 4 together. And we'll get as much of this done as we can before folks have to leave. Okay. So it says the frequency distribution shown here illustrates the number of medical tests conducted on a randomly selected group of emergency room patients at a local hospital. Okay, so they went to the ER and 33.3% of the people didn't have any tests done for whatever reason. And then there was 13% of people that had 5 tests done. They just couldn't figure out what was going on. Okay, so it says, explain why it is safe to assume that the number of tests performed on a patient is disjoint. Well, you either had one test or you had 5, right? You couldn't have had both. So you fall in one category or another. Not both. Okay. Selecting just one patient at random, find the probability that the patient did not have exactly 4 tests. Okay, and it's exactly and did not. So this would be the probability of 4 tests complement. Right, did not have. So that means we can use the complement rule and say 1 minus the probability of 4 tests. So we can add all the ones that were not 4 tests, or we can just say, let's just take 1 and subtract the 4 tests, because we know for a valid probability distribution, they have to add to 1. So we could just pull that 1 out and say 1 minus the 0.093. And we get the 0.907. Okay, so that's using our complement rule. C says, selecting one patient, again, find the probability that the patient had at least 1 test done. Okay, at least 1 test. So the probability of X being at least 1 test. Okay. So at least 1 test means that we can do 1 minus the probability of no test. Right? So we could add them all up, or we could just say, let's just get rid of the 0.333. 0.333, which is 0.667. D says, explain why it is safe to assume in this context, the number of tests performed from one patient to the next is independent. Well, hopefully, whatever I go into the ER for would not have a changing the probability of whatever Arshner might go to the ER for, right? Unless, of course, I don't know, maybe we both ate the same food and we both got food poisoning, right? Then there might be some relationship, but we really, one patient to the other should be independent. To the next. Should not change the probability. Okay. So now we're selecting 2 patients. Okay, so N is 2. Find the probability that both patients had more than 3 tests. Oh, geez. So this would be the probability of X being more than 3 tests times the probability of X being more than 3 tests. Right, because this would be patient 1, patient 2. And I'm saying that because, like, for my brain, when I was first learning this, I had to like separate it out. Some of you might be a little bit ahead of me on that. So this is patient 1, this is patient 2. Okay. So we could just say probability of X being more than 3 tests squared, right? Because there's 2 patients. So more than 3 tests would be not including 3, but more than 3. So that'd be 4 or 5. So that would be 0.093 plus 0.130 squared. And so that, if we add those, that's 0.223 squared. And that comes out to be 0.0497, I believe. 0.223 squared. F says, now we're selecting 4 patients. So pay attention on your worksheets too, because there are parts where we're just talking about 1 patient and then we get more and more. Excuse me. So this time we're selecting 4 patients. So N is 4. It says, find the probability that at least one of them had 2 tests. So at least one had 2. So the probability of at least one had 2 tests. Okay. Of the 4. So that means we're going to do 1 minus let's write this at least 1. So that's 1 minus the probability that none had 2 tests, which is 1 minus not 2 to the 4th. Okay, so that's 1 minus not 2 is going to be 1 minus 2 to the 4th. So 1 minus, and 1 minus 2 would be 1 minus 0.148, and that's to the 4th. So we want to be the not 2, not 2, not 2, not 2, and subtract that from 1. And so that is 0.852, right? So 1 minus 0.852 to the 4th. You can do this in one step, but you could also do 0.852 to the 4th. And so that would be 1 minus 0.5269. And so this comes out to be 0.4731. So these definitely do take a little bit of time, these ones. Any questions on that one? Okay. So let's do one more where we've got some questions surrounding these two-way tables, because they get a little bit tricky. And I know there's some two-way table questions in your worksheets that are due Friday night. So don't hesitate to email me to schedule Zoom time for office hours if you want me to help you on your worksheets, or scheduling time with a tutor. This is a good time for me to show again how to get to the tutoring session. So let me show that on our website. Or sure, did you end up having a tutoring session with Stephen? Was it amazing?
Mhm. It really helped. I think I'm gonna do one again tomorrow.
There you go. Everybody should be taking advantage of the tutoring session. So if you go to the search tab and type tutor, whoopsie, tutor. actually a tutoring center. And the first thing that will come up will be Center for Student Success. If you click there and then scroll down in the search button, you can either scroll through what's available or just type MAT for math. And then the class that you're in is Math 133. And I'm going to go through real quick the really good ones. Abby Frew, I do not know her personally, but her dad is one of our vice presidents. Abby is an amazing tutor. She won Tutor of the Year award, Student Worker of the Year award last year. Caitlin, I do not know, but any of our tutors would not be tutors if they weren't great. So I'm going to let y'all know that. Stephen, I do know personally. He was my own 7 weeks, so took the same course as you, tutor last winter. He's amazing. Arsenal just had a session with him and said he's great. Taylor Hudson, again, I don't know her. April was a tutor in my class last semester, and she is great. So highly recommend them all. You just click on whomever you choose and maybe kind of go through them all and just see their different availability because they are all different, available at different times. You can do group tutoring with Stephen, 30 minutes, 60 minutes, or a quick, can we meet now? Everything is due and I'm stuck. Sometimes it happens, right? So if you click on that, let's say I'm going to do the can we meet now? I'm stuck. And let's see what's available. So he is available. Look at, he's got Saturday and Sunday times available this week, even though it's Memorial Weekend. So if you weekends work for you, click on Sunday and see he's available all of these times. And if there's times a day that work for you, and if they consistently work for him, you could just say, hey, can you block me off for every Tuesday at 5 p.m. and he'll block you off. So it's fabulous. I definitely recommend taking advantage of it. Okay, so back to our last problem here on page 507. We're going to look at people's blood types. People's blood types. So besides the 4 different blood types, there's also this RH factor. And I don't know the total difference between RH positive and RH negative. I do know if you're RH negative when you're pregnant, I think you have to have a special test on. I'm not really sure, to be honest. I know there's something to do with that. Okay, and this is for people living in Quebec, Canada. So we have type O, type A, type B, type AB. And I think blood type is so interesting because I know that they have been collecting data on folks with COVID and their severity of symptoms and seeing if there's a relationship between different blood types. And I think people with O negative maybe, or O, I know O for sure, but I think it's O negative, tend to have a less severe symptoms than other folks. And apparently type A positive tend to have worse symptoms. And I haven't, lucky me, I have not contracted it. So, and I have A positive, but I also take as a side vitamin, vitamin D, which they highly recommend because they're saying that there is a relationship with folks that don't have sufficient vitamin D levels in their blood, have a harder time fighting off the symptoms. So just wanted to throw that tidbit out there. Okay, so we need to fill in the rest of the table. So we're going to go ahead and add these rows. Okay. Okay, so when we add up our columns and our rows, this is what we get. So B says, the person is a universal donor. So notice that parts B through E, we're just choosing one person. So one single person. What is the probability that this one person is a universal donor? O negative. That means they can donate to any blood type, which is so cool. Universal donor. If you're an O negative, your blood is very much needed. So O negative is this specific cell right here, this 0.07. And these are already probabilities, so we don't have to divide by anything, because if you divide by 1, it doesn't change, right? So that's the cool thing there. C says, what is the probability that the person is Rh positive? So that would be anybody that's Rh positive. So all the way over here. So it looks like 85% of people are Rh positive, so 0.85. What is the probability that the person is A positive or B negative? And you can't be both, so they're definitely disjoint, so we can add them. So A positive is 0.36 plus B negative is 0.015. So that would be 0.375. I added those correctly. E says, what is the probability the person has type A or they have a positive Rh factor? So this is not disjoint. So we are going to have some overlap. So type A is 0.42 plus, so I'm going to write, that's the probability of type A plus the probability of being a positive Rh factor. We said it was 0.85 minus the probability of both. So this is the A people, right? And then this is the Rh plus people. So this cell right here is the overlap. So we have to subtract 0.36. So we're going to get on our calculator, 0.42 plus 0.85. And you know that you would make a mistake if you added those together and just said, oh, it's 1.27, because we can't have bigger than 1, right? So it's like, oh, there must be some overlap. And there is 0.36. And so the likelihood of being either A blood or positive Rh would be 0.91. So make sure you're recognizing when you've got some overlap. Okay. Now the second piece is F, G, and H are all choosing 3 people. So N is going to be 3. So it says, what is the probability that all 3 people have type B blood? So that would be probability of B to the 3rd, right? Because N is 3. And so having B blood is 0.09, it looks like. So 0.09 cubed.
Professor, I just wanted to say I am heading out.
Okay. Be careful driving.
Thank you.
See you Thursday.
See ya.
So this is a small probability. Notice you've got that scientific notation. Whenever you get that, it's not 7.29, it's actually 0.000729, right? So 7, I'm going to write it like this so everybody can see. This is actually a very small number, so 0.000729. G says the first person is O positive, the second is A positive, and the third is B positive. And they all should be independent of one another, so we could multiply their probabilities. And remember, these are very specific with the Rh. So we're looking at O positive, which is this cell, 0.39, A positive, 0.36, and B positive, which is 0.075. And it's very unlikely This is very small as well. Both of these are unusual outcomes, right? Because they're both less than 5%. And then H says, what is the probability that at least one of the people is O negative? So that means mono minus the probability of O negative, not O negative, right, to the third. So 1 minus, and not being O negative is 1 minus the O negative, which is 0.07 to the third. And so not being O negative is 0.93 to the third. And I'm going to find out what that 0.93 to the third is. That's 0.804. Oh, they said 4 decimal places, so 1 minus 0.8044. 0.1956. So being O negative is not super rare because it's 7%, right? But it's pretty rare. AB negative is the most rare in Quebec. So, and Quebec isn't, I would say, the majority of people that live there are French, right? So that they already have a particular ethnicity. So I'm with COVID and everything going on, I've really been enjoying like researching ethnicities and their blood types and all that. It's very interesting. So that concludes everything I have for chapter 5. Like I said, I will have a link for all of my live session for chapter 5 from the winter, just so you've got a variety of some things to look at. And if you have any questions, you can reach out. And did you have any questions in particular today?